Hello, so this is a fairly impromptu video. I haven't made a video for this channel for a bit, because the last one I did was fairly lengthy, and so I thought that that would suffice for the channel for a while. However, it seems a good time now we're entering into the summer to bring out a new video, particularly because I've been doing lots of reading of some new quantum mechanics books. And in this video, we're going to be looking at Heisenberg's uncertainty principle in a nutshell. What I won't be doing, unfortunately, for those particularly of a mathematical persuasion, is I won't really be deriving Heisenberg's relation. I won't be explaining it particularly rigorously, but I would like to show what it predicts, why it's important to quantum mechanics, and then at the end of the video we'll be looking at how we can really use it to work out what kind of quantum mechanics we have to worry about, and also use it to predict the end of quantum mechanics, by which I mean predict the point at which quantum mechanics should break down, although we will be discussing that very qualitatively. Heisenberg's uncertainty relation, as well as being the founding, well, kind of governing thing in quantum mechanics, it also predicts its downfall, if you like, at certain energy scales, as we'll come on to at the end of the video. So, the main core equation of Heisenberg's uncertainty principle, at least for position and momentum, is the equation I have on the screen. So these triangles in the expression mean uncertainty. And by uncertainty in quantum mechanics, unlike in classical physics, we mean how poorly things are defined. So uncertainty in quantum mechanics means that the particle or object in question actually physically behaves like its properties is smeared out between one value and another. So it actually says a lot about the mechanics of the object, what it is actually doing. So it's a real physical uncertainty in that the particle behaves as if it doesn't know its value within a particular bound. It's not just our lack of knowledge of the state of the particle. So that's important to make clear, and we'll see examples of that in a bit. So we have the uncertainty in the position x multiplied by the uncertainty in momentum along that spatial axis. So the uncertainty in momentum, at least the x component of momentum, strictly it's greater than or equal to, but for particular reasons in the universe it tends to be approximately equal to a constant, which is very small. But the important thing is that uncertainty in position multiplied by uncertainty in momentum is proportional to a constant. And a good way to understand the physics of this equation is to look at two extremes. So one extreme is where we have a completely free particle, or at least it's very free, so it's allowed to roam across a large region, allowing delta x uncertainty in position to be quite large. The other extreme is where the particle is quite confined by physical forces, so delta x tends to be small. So if we look at the first extreme where delta x is large, well, in this case delta x being large will mean that the particle acts like it's quite spread out in space. Bearing in mind again the uncertainty in here is related to the fact that the particle itself doesn't know it has a position within a particular range. And because delta x, that range is quite large, it means that the particle actually physically behaves to a large extent as if it is spread out across a large region of space. And using our equation, if delta x is large, then because delta x delta p must be about equal to a constant, it must mean that delta p tends to be quite small. And what that means is, to a large extent, a particle has very well defined momentum. So really know where the particle is. The particle itself doesn't really know where it is, but the particle is moving with pretty confident knowledge about its momentum. Um, and because of early kind of effects that have been observed in quantum mechanics, like the diffraction of electrons, where electrons spread out and act like waves, it was found that actually the momentum of a particle relates to its wavelength. So if a particle has well-defined momentum, it has a well-defined wavelength. And we might ask, what kind of thing is distributed across a large region of space and has a well-defined wavelength? Well, it's a wave, and particularly a wave that is periodic and never tapers out. And the simplest version of such a wave is a wave composed of like one sinusoidal term, and so it's a monochromatic wave. It's a wave where the entire wave can be expressed as a sine or cosine function with a continuous wavelength throughout the entire spatial region we're interested in. So from Heisenberg's uncertainty principle, we can reason that a free particle should pretty much act like a monochromatic wave, which is indeed what we observe. When we send free electrons through graphite at high speeds, we see that they diffract and interfere just like waves, and waves with well-defined wavelengths. Now, the other extreme to a free particle is a very confined particle. Now, if a particle is very confined, then at very best, delta X is quite small. And if delta X is quite small, then delta P becomes quite considerably large. And what that means is that now there's a huge amount of range allowed by quantum mechanics about the momentum of the particle, so the average momentum is going to be much higher than what we might expect classically, and so effectively, at least on average, a particle will gain energy. So the more we confine a particle, the more energy it gains, and that could even mean it starts moving relativistically, in which case we have to take account of relativistic equations when we're doing quantum mechanics, but we can still preserve the general structure of quantum mechanics. Or perhaps the particle gains so much energy, we confine it so tightly that the particle actually gains enough energy to convert this gained energy into rest mass of other particles, meaning that we start producing particles, and when the particle number isn't conserved, we have to abandon even the general framework of quantum mechanics and use quantum field theory instead to describe what's going on. So we've already seen here that kind of it's fine quantum mechanics if you have a free particle, and it's fine if it's confined, and it's fine even if it's confined to the point where the particle becomes relativistic, although then we have to include corrections. But the moment particle produces new particles, so if we confine a particle enough, we have to abandon quantum mechanics entirely and use quantum field theory. And I'll be explaining a bit more, well, at least developing this a bit more in the next slide, where we'll kind of summarise how Heisenberg's uncertainty principle really leads to an idea of how applicable quantum mechanics is and where it begins to break down. So, firstly, as we mentioned, a particle when it's free should, or at least is allowed to by Heinsberg's uncertainty principle, act like a free particle. Sorry, not act like a free particle, of course it would if it's free. I mean act like a monochromatic wave. And it was actually something that de Broglie predicted. He predicted this when he was deriving an equation, or at least suggesting an equation based upon observations of the photoelectric effect. So in the photoelectric effect, it was observed that that higher frequency versions of visible light, but still kind of electromagnetic waves, the same kind of thing as light, display particle properties. So it's known that waves can display particle properties, and so what de Broglie postulated was particles might be able to display wave-like properties. And he gave a formal relationship between the wavelength and momentum called the de Broglie wavelength. And the de Broglie wavelength actually matched later experiments, and it was part of the thing that whole kicked off wave-particle duality and early quantum mechanics, when we from this started developing equations of motions for such particles acting as waves. Equations like Schrodinger's equation, and then separately Pauli was working on other aspects of quantum mechanics, and then it took Dirac to actually see that Heisenberg's and Schrodinger's formulations were essentially the same thing using ideas in linear algebra. But the entirety of quantum mechanics really started off with thinking of waves behaving as particles in the case of the photoelectric effect, but also equally as crucially particles behaving as waves. So Heisenberg's uncertainty principle really underpins the start, or underpins the phenomena that began the start of quantum mechanics, at least when it comes to particles, or classically particles anyway. But we've seen that when we confine something, the energy of it should increase. And indeed, we see that, for example, with atoms. So if we've got quite a small atom, the electron is quite confined because the atom is quite small. And therefore the electron actually has a lot of energy. As you go further and further out, the energy of the electrons actually decreases in a sense. I mean, it's complicated by other things, particularly because the kind of energy we're talking about there is potential, and so it gets quite complicated. But it's easier to see if we trap a particle in a box. If we make that box smaller, or if we have a free electron in a wire and we make that wire smaller, the actual energy of the particle will increase. And quantum mechanics can deal with this. It's just, in the case where we're confining it, the particle doesn't behave quite like a monochromatic wave, but it still behaves as if it's more spread out than a classical particle, because a classical particle has well-defined position, and providing the momentum uncertainty, we restrain it to be, not infinite, then there is still some uncertainty in position, so it's still not quite as well defined as a classical particle, so it's a bit spread out, but it's more localized than a monochromatic wave. And in this instance, we have to worry about equations of motions, therefore, that are somewhere between describing the particle like a classical particle and describing it as if it was a classical monochromatic wave. And the equation that does this is Schrodinger's equation, but just with a term that includes classical forces acting on the particle, or more specifically, classical potential energies associated with those forces. Now, if we confine the particle even more heavily, then the particle on average will gain so much energy that it might actually start to move at relativistic speeds. And in that case, we can still use quantum mechanics providing the relativistic effect is small, and until you get to, pretty much like 90% of the speed of light, the relativistic effect is very small indeed. Well, at least small. So providing the particle isn't moving at a significant fraction of the speed of light, and when I say significant, I mean, at least, above 50%, then we can treat the relativistic effects as kind of additional small changes on top of a non-relativistic version of quantum mechanics. And the way that we do this is we use something called perturbation theory. But importantly, Heisenberg's uncertainty principle still allows us to use standard quantum mechanics. It just ends up indicating that the particle might move relativistically, so we have to fine-tune, if you like, the equations. Not artificially, using well-defined methods that work even in non-relativistic cases, in that perturbation theory applies to non-relativistic cases as much as it does to perturbation in the case of relativistic circumstances, but we can still use the underlying framework of quantum mechanics. But if a particle is extremely confined, then it might gain enough energy to convert this excess energy into the rest mass and mass of other particles. So it might start producing new particles as we confine the original particle, more and more. And in this instance, we've got the number of particles changing. Now, quantum mechanics works in something called a Fock space. That is a space where the number of particles is constant and doesn't change. However, in situations where the number of particles is changing, quantum mechanics in its non-relativistic form can't deal with it, because indeed the creation or destruction of particles is ultimately a relativistic effect. So if we're having creation or destruction of particles, or in our case it would be creation because we're creating enough energy to convert into rest mass, or at least causing the particle to gain enough energy to convert some of that into rest mass of new particles, that we do have to abandon standard non-relativistic quantum mechanics and use a relativistic version that has, from its setup, different axioms allowing for the creation or destruction of particles, whilst preserving a lot of the ideas in quantum mechanics, and that new setup is called quantum field theory. It's something I've done a few videos on. I hope to do some more at some point on quantum field theory, but Heisenberg's uncertainty principle, as we can see here, does not only just predict the beginning of quantum mechanics with phenomena like the wave-like behaviour of particles, it also predicts the end of quantum mechanics in terms of the need for a new theory, which has become quantum field theory. So I hope this video was helpful. I'm aware that it might not be particularly smooth or neat. I try to do videos at least as much as possible in the first or second attempt, unless something technologically goes wrong, because I want to keep it fairly natural. It does mean that it's perhaps a bit less smooth, but then it means that kind of like it comes across naturally, and also I'm thinking about what I'm saying as I'm saying it, and I don't enter into the trap of just saying lots of stuff without kind of thinking it through. But I hope to make some more videos soon-ish. I would like to make them fairly soon, but I'm reading a couple of books on quantum mechanics, so I really like to make some videos based around those books and to get a flavour for those books. I'd like to finish them, but I'm not particularly a super speedy reader. However, I've got a few days towards the end of the month which I can devote to looking through them in a bit more detail. So hopefully another video coming out soonish, and wishing you a good week, yeah, lots of fun, and hopefully enjoy the sunshine too. Don't spend too long on YouTube. Anyway, see you in another video soon.